Okay, I shared with you this OneNote screen. Can you see that?
Yes, we can.
Yes.
Okay. You know, yesterday we were learning Lorentz series, how to find Lorentz series of a given function for a given region. And a Lorentz series is a series like this. This is the whole yesterday what we did was about this series, Lorentz series. And even today we will be using, and also in the next lecture.
Doctor?
Yeah?
Could you make the screen wider? It's hard to see.
It is hard to see.
Yeah, very small, very narrow.
And what about now?
Yes, better, thank you.
دكتور. دكتور.
Yeah.
What happened?
Oh, by mistake, I pressed the power button of my Surface Pro, and then it was turned off. Is it okay now?
Yes, now we can see
It's perfect.
the notes.
Okay. Let me also open this book. You know, we were finding a series of this form. a series like this, which can be written as in this mission notation. So let me put them together. We have this Laurent series. In this Laurent series, this part, it has two parts. This part is called principal part. When we have z minus z naught power negative, or we write actually in the denominator, this is called principal part. And the other part is called analytic part with the positive powers. So a Lorentz series has two parts, principal part and analytic part. Now, principal part tells us about the singularities, if there is a singularity or no singularity. Okay. When we see a function, when we see some function, we can tell that this function has a singularity. Now that singularity is has a different is of different types. It is a removable singularity, it is a pole, or it is an essential singularity. For example, sine of z over z. This is not defined at z equal to 0. Z equal to 0 is a singularity. But when we expand sine z, we get z minus z cube over 3 factorial plus z power 5 over 5 factorial. And when we take this over z inside, we get 1 minus z square over 3 factorial plus z 5 over 5 factorial. So now this singularity is gone. So this function sine z over z has a removable singularity. It has a singularity, but that is removed. And maybe it is not removed. It is still a singularity. Then it will be a pole of order 1, pole of order n, or it has essential singularity. So we are now discussing the isolated singularity, and types of this isolated singularity. We say classification of isolated singular point. Classification of isolated singularity, or we call this as isolated singular point. Okay. Suppose we have z equal to z naught, an isolated singularity. Suppose z equal to z naught is an isolated singularity of some function f of z. Then number 1. Let me save my time of writing and do this. Number 1. If the principal part is a 0, that is all the coefficients a sub negative k in here, this is equation number 2, in 2 are 0. Like I gave you example of sine z over z. So there is no more principal part, only analytic part is there. Then we say that it is a removable singularity. It was a singularity, but now it is removed. And second singularity is that if there are finitely many terms, if there are finitely many terms in the principal part, finitely many terms in the principal part. Number 2, if the principal part contain a finite number of non-zero terms, yani 5 non-zero terms, 10 non-zero terms in the principal part, 100 non-zero terms in the principal part, then the singularity is called a pole. If there is no more principal part, then it is called removable singularity. If there are finitely many terms in the principal part, for example, there are 100 terms, and after that everything is 0. Yani a negative 100 is 0, then a negative 101, a negative 102, a negative 103, all are 0. We say that a sub k, negative k is 0, and a sub negative n, when n is greater or equal to k plus 1, they are 0, and this is not 0. Yani the maximum k for which a sub negative k is not 0, and after that a sub negative n for n greater or equal to k, after that all the coefficients are 0. So in this case, the singularity is called a pole, and that number is called order of the pole. If it is 100 or 5 or 1 or 2. But if it is 1, then we say it is a pole and is a simple pole. It is a simple pole. In a minute, I will give you examples. But now the third case is that the third case situation is that the principal part has infinitely many terms. If the principal part contains infinitely many non-zero terms, then it is called essential singularity. So a singularity is one of these types: removable, pole of order n, and essential singularity, and this depends on the principal part of the Lorentz series. For example, if you look at this a kind of a table, it will be more clear. It will be more clear if we look at this table. Number 1, we have a naught plus a1 z minus z naught plus a2 z minus z naught square. So there is no principal part. So z equal to z naught is a removable singularity. Second line, a sub negative n is 0 is not 0. So in the principal part, the largest value of the index is n with a sub negative n, or we can say the largest power of z minus z naught in the denominator, yani principal part. If the largest power of z minus z naught is n in the principal part, of course z minus z naught will be in the denominator. Then there is a pole of order n. And if the largest power of z minus z naught in the denominator of the principal part is equal to 1, then we say it is a simple pole. And if the principal part is going up to infinity, there are infinitely many terms, then we say it is a essential singularity. If any of this is not clear, please tell me, I will explain it again. Okay. Maslan, example, f of z is equal to sine of z over z. When we expand this, we get 1 over z bracket z minus z cube over 3 factorial plus z power 5 over 5 factorial plus minus so on. This can be written as 1 minus z power 2 over 3 factorial plus z power 4 over 5 factorial z power 4 minus plus so on. So here we see that z equal to 0 is a removable singularity. But if of f of z is sine z over z square, then we will get 1 over z minus z over 3 factorial plus z power 3 over 5 factorial plus minus so on. And in this case, can someone tell me what is z equal to 0?
Simple principle.
Sorry?
Simple principle. Both.
Principle is a
Simple
is
both.
a simple pole. Very good, excellent. Is a simple pole. And now f of z is equal to z square sine of 1 over z. Sine of 1 over z. So what this will be? Z square, then 1 over z minus 1 over 3 factorial z cube plus 1 over 5 factorial z power 5 and so on. And when we multiply z square inside, we get z minus 1 over 3 factorial z plus 1 over 5 factorial z cube minus 1 over 7 factorial z power 5 minus plus and so on. Now you see the part which has a z in the denominator, yani the principal part is going up to infinity, and it has infinitely many terms. So in this case, z equal to 0 is an essential singularity. And here you see we have 1, 2, and 3 examples. In number 2, if we have z power 3, z power 4, z power 5 in the denominator, then we will not have a simple pole, we will have a pole of order bigger than 1. If we have, let me make it in red color. You see I circle sine z over z square in red color. If in the denominator we do not have z power 2, we have z power 3. Then z equal to 0 will be a pole of order 2. And if we have z power 10, then z equal to 0 will be a pole of order 9. Because after simplification, we will have over z power 9. So these are about singularities of a function. The second thing is zeros of a function, and that depends on the analytic part. That depends on the analytic part. So second thing is zeros. First singularity, then zeros. Z equal to z naught if is a zero of a function f. Z equal to z naught is a zero of a function f if f of z naught equal to 0. And if f of z naught is 0, f prime at z naught is also 0, f double prime at z naught is also 0, and then we reach somewhere that f n minus 1 at z naught is 0, but f at n, f nth derivative at z naught become non-zero. Then z equal to z naught is a zero of order n. We call this as a zero of order n. If up to up to n minus 1 derivatives are 0 at z equal to z naught. Derivative n minus 1, but order of the 0 is n, because we are starting from 0th derivative up to n minus 1th derivative. And this depends on the analytic part of the Laurent series. For example, let me just say copy and paste this thing. You see here, what is this? This is the analytic part of the Laurent series. This is analytic part of the Laurent series. Here, the Laurent series is starting from z minus z naught power n. There is no term before that. Z minus z naught power 1 is not there, 2 is not there, 3 is not there. So it is starting from z minus z naught power n. So this series, in which there is no principal part, but here is analytic part, and analytic part is starting from z minus z naught power n. Therefore, we say that z equal to z naught is a 0 of order n, because when we replace z equal to z naught, f of z naught will be equal to 0. So, other words, we can say it like this. Here, a sub n is not equal to 0. Maybe an plus 1 is also 0, an plus 2 is also 0. Yani there is no term with power n plus 1 with power n plus 2. But the first power of z minus z naught, which is not 0, is n. Then it is a pole of order n. Then it is a pole of order n. And similar examples are given in your book. Like I gave you these examples. For the singularity, similar examples are given in your book about pole. Pole is a 0. And somewhere before we have learned about these poles. Now there is another way to find a pole when we have a function given in rational form, and this is given by theorem. What is this theorem? If f and g are analytic at z naught, individually both are analytic, and f has a 0 of order n at z minus z naught, and g at z naught is not 0, then the function f of z equal to g of z over f of z has a pole of order n at z naught. Okay, that makes sense. Pole, not 0, pole. Yani this is f of z equal to g of z over f of z, and f of z equal to 0. Yani 0 of the denominator is the pole of the whole function. Let me rewrite this again. We have f of z equal to g of z divided by small f of z. Now g at z naught is not equal to 0 and z equal to and z equal to z naught is a 0 of f of order n. Yani z equal to z naught does not make g equal to 0, but it make f equal to 0 and f, this is order n0. Then what is z equal to z naught of f of capital F of z? It is a pole of capital F of z. It is a pole of yani 0 of the denominator. Again, 0 of the denominator is a pole of the function. And if it is a 0 of order n of small f, then it is a pole of order n of capital F. But there is one condition. Numerator function at z naught should not be 0. Otherwise, we will have 0 over 0 form. For example, here just by looking, we can say about this function that, let me say this as example. Okay, what are zeros of Mokam denominator, Shabab? Zeros of the denominator z equal to 1, z equal to -5. Let us call them also simple zeros. Any 0 of order 1, like we call it pole. Of order 1. And z equal to 2 of order 4. And none of these 1, -5 and 2 make numerator equal to 0. So what we will say, to z equal to 1 and z equal to -5 are dash dash of capital F of z. Tell me, Shabab. Someone? No one? Z equal to 1 and z equal to -5 are zeros of the denominator of order 1. Then what are they of capital F of z? Poles. Simple poles of capital F of z. And z equal to 2 is a pole of order 4 of capital F of z. So this was about poles and zeros of a function. Now let us see some questions from exercise 19.4. Okay, not much has to be done in these questions, I mean in calculation wise. So let me just copy and paste from the book and then explain this. You are seeing question number 1, e power 2z minus 1. Now e power 2z, when we replace z equal to 0, we get 0 over 0. So and we can also look at this. Okay, when we look at this one, we see that z equal to 0 is a 0 of the Muqam denominator. Denominator is 0 at z equal to 0. But at z equal to 0, numerator is also 0. So this last theorem here, 19.4.1, will not be used here. So what should we do? We should use what we learned before. So first of all, we expand e power 2z, and it will be 1 plus 2z plus 2z square over 2 factorial plus 2z cube over 3 factorial and so on. When we take 1 over z inside, we get 1 over z plus 2 plus 2z whole square over, not whole square, actually no, we need to expand. We have 2 power 2 and z over 2 factorial plus 2 power 3 and z square over 3 factorial and so on. So we see that z equal to 0 is a simple pole of f. It is a simple pole of f. It is a singularity, but a simple pole. Then we have some function where we need to determine the 0 and what is order of the 0. Here, let us see what is question number 4. What is question number 4? And I suggest you, if you have book, you can open your book and that will help you. That will help you. Question number 4. Let me stop writing, copy and paste. So here is question number 4. In question number 4, let me do it again. Yeah. In question number 4, we see f of z equal to z power 4 minus 16. Now this we can write as z power 2 minus 4 and z power 2 plus 4, which we can write z minus 2, z plus 2, z minus 2i, and z plus 2i. So we see here that f of z has zeros of order 1 at z equal to plus minus 2 and plus minus 2i. Plus minus 2 and plus minus 2i. And I hope it is clear. If not, tell me.
Dexter, can you go back to question 1?
Above. Okay.
Why we don't subtract 1 from the e to the power z?
Because it has power 0. So it will be 1.
1, but in the function there is minus 1, so...
Oh, you are absolutely right. I missed this. I missed this part. Thank you. We have minus 1 also. So with the minus 1, what happened? 1 and 1 cancel. 1 and 1 cancel. And after that, when we divide by z, we get 2. You are absolutely right. 2 plus 2 power 2 and z over 2 factorial plus 2 power 3 z square over 3 factorial, so on. So now it is changed. What is z equal to 0?
Removable.
Excellent, excellent. So I missed that minus 1. I missed that minus 1. So, and also now we can see if there is no minus 1, it will be a pole. And if there is minus 1, it is a removable singularity. That was my mistake. I missed that minus 1. I didn't look at that. Okay, now we have zeros in question number 4. And what is question number 5? It is z power 4 plus z power 2. So that z equal to 0 is a 0 of order 4. That is very simple function. And then we have question number 6. Question number 6 has z plus 9 over z. This is question number 6. Now we can write this as z square plus 9 over z. Z square plus 9 over z. Now can we factorize numerator? Is there something which can make numerator equal to 0?
Yes. 3i.
Which can be written as z plus 3i, z minus 3i over z. So f of 3i equal to 0. F of negative 3i is also 0. F of 3i is 0. F of negative 3i is also 0. Now, is this a 0 of order 1 or maybe of order more than 1? For that, what we do, we find f prime of z. No, all z plus 9 over z or z square plus 9 whole over z or z plus 3i, z minus 3i over z. All these three are equal. They are not three different functions. They are same. So take derivative of any of them. So let us take derivative of first. It will become 1 minus 9 over z square. And we see that f prime at plus or minus 3i will not be equal to 0. Therefore, we can say that 3i and minus 3i are zeros of order 1. Z equal to 3i and minus 3i are zeros of order 1. Order 1. Okay. Now there are some other functions where you need to expand and then you will be able to tell that what is order of the 0. For example, let me do question number 9. When z is 0, f of 0 is 0. Yani first thing to make sure that z equal to 0 is a 0, we check that function is 0. Yeah, when you put z equal to 0, if it is 0. But what is order? We can do by taking the derivatives. But you know, cosine, when we take derivatives, cosine z becomes sine z, then sine z becomes cosine becomes sine becomes cosine. So this will not end. Therefore, we do not do this one. We do this. Z, we write its series. 1 minus cosine of z square. The series for cosine is z is 1 minus, so become plus z power 2 over 2 factorial. Yani z square power 2 over 2 factorial minus z square power 4 over 4 factorial. Actually, it is 1 minus z square over 2 factorial plus z4 over 4 factorial. Since we have here what we have minus outside, so it become minus plus minus plus and plus minus so on. Now this 1 and minus 1 cancel and we take it to inside, we get z power 5 over 2 factorial minus z power how much? 9 over 4 factorial plus minus so on. From here, we can take z power 5 mushtarik. Inside it will be 1 over 2 factorial minus z power 4 over 4 factorial plus minus and so on. Now we can say that z equal to 0 is a 0 of f of order 5 and this result is from this expression. Let me say equation, let me put in this circle. I hope you are seeing that I put this big representation of f in circle in red. So from here we get the last result of this question number 9. If something is not clear, tell me. Yes, Shabam. Any question?
Clear, Doctor.
Good. Okay, you look at the questions and let me know if any other question you want me to solve for you, show you its solution. What I am looking in the book, there are several other questions here. Now, next set of questions is from 13 up to 24, where we need to determine pole. And that is similar to what we did before. Here, let me copy and paste question number 14 for you. Question number 14 is here. We have a 5 minus 6 over z square. Okay. Now, we can write this as five z square minus 6 whole over z square as g of z over f of z. F at 0 is equal to 0, and so z equal to 0 is a 0 of f. And what is order of order 2? But we also need to make sure that g of 0 is not equal to 0, and it is clear. G of 0 is equal to negative 6, which is not equal to 0. So z equal to 0 is a pole of order 2 of capital F. Oh no, we have written here f of z. So let us give this different name, like g of z and h of z. So instead of this f, let us call this as h. So z equal to 0 is a 0 of order 2 of the Muqam function, denominator function, but numerator function is not equal to 0 at z equal to 0. Therefore, z equal to 0 is a pole of order 2 of the whole function. Is it clear, Shabab? Tell me if it is not. Then there are some other questions here. Question number 17. Let me do this question number 17. F of z equal to tan z. And you know, tan z can be written as sine z over cosine z. Sine z over cosine z. Now here we are looking for the singularities. Yani, what they are saying, determine the order of poles, yani singularities. So we look at the denominator and we know that cosine z equal to 0 for z equal to what? For z equal to what? Sine z or cosine z?
Pi over 2.
Then n plus 1 pi over 2.
N plus 1 pi over 2. Z equal to 2n plus 1 pi over 2, where n is 0 or plus minus 1, plus minus 2, and so on. And sine of 2n plus 1 pi over 2. When n is 0, it is 1 pi over 2. So 1. When n is 1, it is 3 pi over 2 minus 1. When n is 2, it is 5 pi over 2 minus 1. So it will be equal to plus or minus 1. Yani not equal to 0. So z equal to 2n plus 1 pi over 2 for n equal to 0 plus minus 1 plus minus 2 are simple poles. Okay. And if we have cotan of z, then what will be simple poles? N pi, because it will be cosine over sine. So sometimes we have things like this. And what is after this? We have some other functions. You try to solve them. I have done so many questions here to show you their poles, their zeros, and you can do maybe more. Let me see if there is some other function. Or you want me to show you a solution of some other question, but no, it is time now. So we have done this 19.4. Now 2 more exercises are left and 2 more days are left. And inshallah, we will cover those 2 sections on Sunday and Monday. You must have started preparing for the final. If not, you